right, folks, exponential growth. So what is kind of fun about exponential growth is that I know it's so much fun. Marley, there no, if you could just tell people to stop chatting, I would appreciate that. Yeah. Okay? Like Marley was sitting there quietly trying to listen. Yeah. All right, exponential growth happens in nature. What is one example? So, exponential growth, we did it as a practice with the penny problem. You get 1 penny one day, 2 pennies 2 days, 4 pennies next day, 8 pennies the next day. What was the base of that exponential function? 2, because it was doubling. If you got 1 penny one day, 3 the next day, 9 the next day, 27 the next day, what would be the base? Tripling. 3, because it would be tripling. Right? What if you had $20 one day, $10 the next day, $5 the next day, $2.50 the next day? What would the base be? One half. Your money would be halving. Okay? Today we're talking about this, which is something growing exponentially. Tomorrow or actually Tuesday, we're talking about this exponential decay. Okay? And I want to show you a few examples of when exponential growth happens in this world, in nature. Okay. So, one example is cell division, right? We talked about mitosis. So, mitosis, watch this: one cell, two cells. We're doing mitosis, basically, yeah. 4 cell, 8 cell. Now, watch again, Greg, and tell me, does it speed up? Like, are they dividing faster and faster and faster, or are they dividing at the same rate? Same rate, right? Because it takes one cell a certain amount of time to divide. Depends which cell, right? We know certain cells take a really long time to divide. We know some cells do not divide, like your neurons. We know some cells divide very quickly, the ones that need to heal. All right, so we go from 1 to 2 to 4 to 8 to 16. Our cells divide exponentially. Now, what is one factor that this animation does not consider? Pardon? Apoptosis. Do you remember that wonderful name? When cells die. During cell division, if a cell is not formed correctly, it has checks, right? It has flags that say, oh, this cell is too big, deformed, blah, blah, blah. It dies because it's not. So this does not, so it's not like our cells actually double and double and double, because otherwise we would just be growing exponentially, right? There are cells that are dying. And that's a good thing to keep it. Yeah. No, that's not what I want. Okay, here. This is fun. Bacteria growth. Okay, bacteria are cells as well. They're unicellular organisms. And what's cool about them is they grow exponentially as well. Isn't that cool? All right, more exponential growth in nature. Okay, world population actually grew exponentially. Now, this is not a natural phenomenon. Okay, anyone know what caused, or what might be some of the factors that caused this type of exponential growth? The Industrial Revolution. Yeah, what else? Yeah,
Has been a massive extinction.
say it again.
I don't know, there's been extinctions and there hasn't been one in a long time.
Okay, I mean so it's 1800s that we started expanding. So technology, industrial revolution, agriculture, yeah, yeah, medicine, right? We've got this great medicine that people have a longer life expectancy. So our world population is growing exponentially. Now, as you remember maybe from grade 9 biology, something called the limiting, no, what is it called? The limiting capacity? I think it's called. It's, it's a number at which the ecosystem cannot hold any more of that population. And so the population will start declining, right? Because there's only a carrying capacity. That's what it's called. There's only so much that an ecosystem of a certain population that an ecosystem can hold. Do you know what else had exponential growth? Is the COVID cases, right? And what did like I'm not sure what the base is, but do you remember how they were saying if you get COVID, thank you. Is that my phone? If you have COVID, you can pass it to 2 or 3 people. They can pass it to 2 or 3 people. They can pass it to 2 or 3 people. Right? That's representative of the base, somewhere between 3 and 4. And so initially, before we had a vaccine, the growth of the of COVID cases was also exponential, right? Which is interesting. So exponential growth is something we see often. So today I'm going to teach you how to calculate certain features about this exponential growth. All right, let's go to page, is it 12? 14?
14.
All right. So today we're going to be looking at examples of exponential growth. We're going to learn how to model them. Okay, so, and when we say, please stop. When we say, so put your phone away, right? Get your booklet out. If you're doing something that isn't excellent for you, like give yourself the opportunity to learn, folks. Take the earbud out. Earbuds? All right. When we say that we create mathematical models of something, basically we create an equation that can predict how that something changes. So we're going to write equations about certain exponential growth. Okay. We're going to talk about something called doubling time, which we've already talked about. And we also need to convert different times into different units. So hours into years, days into seconds, that kind of stuff. All right. Can I ask you folks to read this part on your own? Okay, I'm going to try to figure out what's going on here. Can you read that little paragraph? All right. Thank you for reading that. So, I'm plugged out. So, exponential growth can be bacteria growth. It could be cell growth. It could be growth of animals or plants, so population growth. But it could also be related to compound interest. Oh my God. Mortgage inflation. So, you could use it with money. You can use it with population growth. So, let's look at an example of population growth. So, we're going to use this equation here. And the 2 is there because we are talking about the doubling time. Right? With mitosis, with bacterias, we know that they double. Okay? Generally, it's not like one cell produces 3. No, one cell dividing produces 2. So in nature, we often experience doubling time. So the 2 represents doubling time. The D at the bottom is actually the time it takes for the population to double. Okay. So basically for mitosis, yeah. For mitosis, the question is, how often do cells separate? If it's every 7 hours, then that is your doubling time. Okay. Next, A naught is the original population or initial or original amount. We'll call this initial amount. So if we're looking at the mitosis video, there was one cell at the beginning. And the A of t, it's a function. It is the amount at a given time. Amount at a given time. Okay, it could be after 3 hours. How many cells will we have after 3 hours? And then this little t is the time elapsed. Okay, let me call the, this is annoying. I didn't want to get this slide in too much more. Hi. I don't know what's going on, but our clock buzzes every minute or so.
No, it's actually not. It's not a bad thing because we have. Yeah, no, we want the parties.
Yeah, if someone can't, that's fine.
Are you talking about? Do you want to pick that?
Oh, okay, perfect. Yeah, perfect. Thank you. Bye. All right, we might have to deal with this buzzing. Thank you, clock. We're still here. All right, dudes, let's do this. Sorry, a few. Let's look at an example of, folks, back here. I know a lot of stuff going on. Let's see how to use this formula. The difference that I want to show is between the T and the D. So the little t is how much time has passed. Okay. The little d is the doubling time. How long does it take for something to double? So if you have a bacteria, how long does it take to go from one bacteria to two bacteria? Okay. So the little t is our independent variable. It's the one that we're choosing. After 1,000,000 hours, how many bacteria will there be? After 10 hours, how many will there be? All right, so we're going to have a lot of word problems. What that means is we're going to do active reading. We are going to underline the important things and circle what we are being asked to answer. Okay, example 1. A certain colony of bacteria doubles in number every 3 hours. Okay, so what does 3 hours represent? The little d. If there are 100 bacteria in the colony to begin with, what does that represent? We start with 100 bacteria, initial amount. We say A naught. When you have a little zero there, sometimes we'll just call it A naught. Initial amount. Okay, so we know 2 pieces of information, actually 3, because we also know that it's doubling time. A, write an equation to represent the growth. Okay, let's start with that. So we know our equation is going to look like this. The amount at any given time t is the initial amount. So that's 100 times 2, right? That's our doubling time. And then we need to change the exponent to the power of t over d. We don't know the time. So it's going to be little t. Well, that's really little. Little t over d. Now that's the doubling time. What is the doubling time? 3 hours. So this is the model. This is the equation that models how these bacteria grow. Okay. Now for B, determine the number of bacteria that would be present after 1 full day. So what is this information, 1 full day? It's 24 hours. And which variable does that represent? T, little t. How much time passed? 24 hours. So now we'll say, okay, We are looking for the amount of bacteria after 24 hours. So instead of writing A of T, I'm saying A of 24. What's the amount at 24 hours? This is not A times 24. It's just saying what is the amount at 24 hours. Okay, so it's going to be 100 times 2 to the power of, and now we add that 24 instead of the T, 24 over 3. We can simplify that. 24 over 3 is 8. And so to find the number of bacteria after 24 hours, we're basically saying it doubled 8 times. Right? Every 3 hours it doubles. Oh, so that was 8 doublings. Okay, well, let's calculate this. 2 to the power of 8. Is it 256? I don't know. 256. All right, so it's 100. Yeah, it's the clocks. And I called the office and they said a lot of clocks are experiencing this. The caretakers are trying to figure it out. Okay, so what did we find out? We have to make sense of these numbers. What we found out is that after 24 hours, how many bacteria are there? There are 25,600 bacteria. Okay, so it's really figuring out how to use this formula. Let's try it again. Yeah. Yeah, please.
So are T's always going to be the same value in the equation? Like the amount of
The little t?
yeah, the little t and the amount of time. Like A of t and then
So this is the input. Remember, when we had a machine, this is representing the input. And where do you put the input? Oh, you put it here. So this is not A times 24. It's just saying at 24 hours, how many bacteria do you have? I could have said A of 100. How many are you going to have after 100 hours? Okay? Yeah, you're welcome. All right, let's look at another one. Okay, so let's do active reading. The human population in August 2018 was 7.6 billion, and it is growing at a rate of 1.09% per year, which represents a doubling time of approximately 58 years. Whew. All right, let's go back. The human population of August 2018. Okay. So this is T naught, right? This is the original time. And 7.6 is A naught. It's the original amount, right? This is not when humans started being, but we're saying we're going to start our timer in August 2018. And it grows at a rate of 1.09. Do you know that this is actually not important? This is the word problem trying to trick you into putting 1.09 somewhere in the formula. The reason that you don't need it is it says, okay, it grows at a rate of 1.09%, which represents a doubling time of 58 years. So this question says, yeah, that's the percent, but really that percentage can be written as a doubling time of 58 years. Okay? Assuming the growth rate remains constant, right? So we're saying same deaths, same growth rate, no pandemic, no food shortages, no wars, all that, right? Estimate using the exponential function how many new humans will populate the earth by 2025. So how many new humans? So we want A at T. And the Earth's population in 1900. So we're actually going backwards, right? We are given 2018, but we're going to work backwards in the second question because we need to find what was the population in 1900. So let's start off by writing down what we know. Okay, so in this case, we're using our population. We're writing a model, AFT. We know our A naught is 7.6 billion. I'm not going to write the billion part. I'm just going to write 7.6. Okay. I know we've got what is going to be the base of my function? 2 because it's doubling time. I will tell you folks, most of the time for exponential growth, it's going to be doubling time. But on the test, I will give you a tripling time question or a quadrupling time question, right? And then you're like, oh, I know she's just telling me to change the base, right? Okay, and then we need T over D. So we don't know the time right now, but we do know the doubling time. And the doubling time is 58 years. Now, the little piece, we're going to make an estimation. We are going to disregard the August part. Okay, we're just going to use 2018 as our T naught. So our time that's elapsed, how much time has passed, is going to be 2025 minus 2018. So I'm ignoring that we started in August, and I'm just saying how many years have passed. Well, that tells me that it's 7 years. Now, we must check if T and D have the same units. In this question, they do have the same units. What is the unit of time that we're using in this question? Years. It could be seconds, hours, days, years. You just have to make sure that T and D have the same one. Yeah, come on up here. All right, so what I want you to do, folks, is, okay, when time is 7, what will we have? So we have 7 over 58. You need to grab your calculator and try this out. I'll give you what the approximate answer is. All right.
It said fill in a box.
Oh, there's no box.
There's no box.
Yeah, so just write a letter anywhere there.
So this isn't like a...
No.
Okay.
Yeah, sorry, the
Yes.
box didn't copy.
Okay.
So like this can be like D,
Oh, right, yeah.
H, F. Yeah.
Thank you.
Okay, so it's really important that you're not using your phone. It's really important you're using the calculator that you will on a test.
Wait, 8.3?
It should be 8.3.
I thought 16.
Okay, so you made a mistake somewhere in your calculations. My question is, Luke, will it change it if you put brackets around your exponent? Okay? What's after the 2? Oh, so what is it? 8.3. Yeah, good.
Oh, is it right now? I thought
Who got 8.3? Anyone not there yet? It wandered to 8.4. What kind of calculator do you have? That's weird. All right. So, yeah. Yes, I will definitely tell you what decimal mark. Yeah. So, let's write our final statement. Therefore, go ahead and write the final statement. And this requires you to understand what the question was asking us for. And I'm going to encourage you to use the word approximately. Do you know what this dot on top of my equal sign means?
Approximately.
Approximately. You use it anytime you did any rounding. You can use different wordings. But it's important that you write approx or approximately. And it's important that you don't leave it at 8.3. 8.3 what? Billion. Right? Remember, we didn't include the billion in the equation. Yeah.
The next question is how many new humans will populate the Earth? Do we have to do 8.3 like minus 7.6?
That is a really good question. We absolutely need to do that. So, this is how, thank you, Sophie. So, this is how many humans there will be in 2025. But the question actually asked, and I overlooked it, how many new humans? So, how do I do that? That's right, 8.3 minus 7.6, which will give me 0.7, approximately 0.7 billion new humans. Thank you. Which is 700 million. All right, we good? Let's try another one. Okay. So here I really want to say that time one, that original time is 1900, and I want to look at the growth. Why can I not say that 1900 is my T naught? What piece of information do I not have? I don't have A naught. I don't have the amount at 1900, right? So I'm going to keep my time, original time at 2018, right? That's my T naught because I know my original amount, which is 7.6 billion. Okay. So this is going to look weird. It's going to feel weird. But my time is actually going to be 1900 minus 2018, same as I did in the other question. The only thing is, what kind of answer do I get? I do. And so if I populate the same equation and we say, okay, A at T equals negative 118. So we're going backwards in time, equals A naught, 7.6 billion, times 2 to the power of negative 118 over 58. Now, there's actually some sense to this. If I were to incorporate the negative into the base, what would that give me? Yeah, I'd get 1/2. You don't have to do it this way. But what we're saying is, well, if we're going backwards along the exponential growth, it's actually going to be exponential decay because we're going backwards. Does that kind of make sense? So this negative is a good thing, right? We're like, oh yeah, that will allow us to actually decrease the amount. So let's see approximately what do we get. Okay, punch it in your calculator. And I will give you the answer because, again, I want you to practice your calculator skills. So you're looking to get an answer of 1.9 billion, approximately.
Is it 1.85?
So in this case, we're just doing to the nearest tenth, but I didn't tell you that. But like 1 decimal, so you're going to round it up.
5?
Pardon?
If it's a 5,
We just round up. It's just regular rounding. It's not like I know in science or physics there's like weird ways. Regular straight up rounding. And folks, now that I've introduced this approximate equal sign, you will lose communication marks if you're not using it correctly. We good? And so does that make sense? Let's take a step back. Does my answer make sense? Put your hand up if it makes sense to you. Okay, so we need to think, what was the question talking about? Oh, well, it's talking about there being 7.6 billion people on Earth in 2018. And they're asking us, how many were there in 1900? And I remember from this population growth chart that the number grew exponentially. So in 1900, we were somewhere here where my cursor is. And that's between 1 and 2 billion. Huh. Well, that's interesting. So yeah, it does make sense. Okay? And now the actual population was 1.65 billion. What could have accounted for the discrepancy? Well, we don't know the rate of death. We don't know the medical technology that came up, other technologies, all that kind of stuff. Okay? But this is a good approximation. All right, let's look at the last question. How much will the Earth's population grow in 1 day? Okay, so my time now is 1 day. Now, this is kind of problematic because my doubling time is 58 years. So we have to convert one of them so that we have the same units. Okay? I will change time into years. So I'm going to rewrite time as 1/365. You could have changed years into days by multiplying it by 365. Again, keep in mind we're not counting the leap year, right? By saying it's always 365. So 1 day is 1/365th of a year. And so we're going to use the same equation. The amount at 1/365th will equal to 7.6 billion times 2 to the power of t over d. Oh, this is so ugly. 1/365th over 58. So ugly. I got to do some work on the side. How do I figure out this fraction? I've got 1/365 divided by 58. Oh yeah, I know how to do this. 58 over 1. I write the reciprocal. And I can multiply the denominators, and I get a really big number. 21,170. So we are raising the 2 to a tiny fraction. And that kind of makes sense because we know that there is going to be very little growth in 1 day. So the 2 has a positive exponent, but it's a really small one. Okay, punch it in. Which equal sign are you going to use? The approximate one. Yeah. And in this case, do not round. Okay, write the entire number that your calculator gives you. Like that.
It's like, is it 7.600248845?
Yeah. I might have rounded a bit sooner. And so, folks, we got something. Looks pretty good to me. I go back to the question and I think, did I answer the question? Do I need to do more work or am I done? Do I stop or not? Really?
Now we have to apply it.
I want to know how much the Earth's population will grow in one day. I don't want to know what the population is a day later. I want to know how much it will grow. Yeah, that's right. That's why I said keep all the decimals. So in one day, wherever you round it to, I'm subtracting that from 7.6. Which is actually 249,000 people in one day. So this model estimates. You got 5 minutes. Where are you going? Oh, you guys got it. Yes, you do have to go. Good luck. This model estimates that in one day, the population grows by 250,000 people a day. Okay. All right, folks. So you have some homework questions on the back. You have the solutions. Your quiz is on Monday. I didn't post a practice quiz. I just posted some I literally cut and paste homework questions and just thought this is a good representation of the questions you should be able to do. Okay. Anyone have questions? I've got some time. Yeah. They're homework questions, so you just go back and yeah. That's right.